Good morning to one and all. Today we are going to discuss about silicon-on-insulator MOSFET by using TCAD tool. I am Dr. K. Srinivasrao, Professor and Head of Microelectronic Division, VLSI and MEMS Research Center, Department of Electronics and Communication Engineering, KL University, Andhra Pradesh. So we will discuss about what is this SY MOSFET and why we need to use this SY MOSFET in the current scenario and what is meaning of the SOI. SOI is a silicon on insulator, metal oxide semiconductor field affected transistor, and you can see the picture here. We have the box which is showing the insulator between the silicon body and substrate. So silicon body is a silicon, it is a silicon material, and we are placing the silicon material on the box. Box is the a kind of a insulator, so that's why we used to call this is a silicon on insulator MOSFET. So this is a kind of technology which is referred to be use the layer silicon insulator silicon substrate in the place of a conventional silicon in entire semiconducting manufacturing. And you can look at the here the top silicon layer we have, and bottom we have the buried oxide, and base we have a silicon. So both the sides we have a silicon, and in between we have a silicon oxide, that is the buried oxide layer, that is the BOX. And in a transistor, if you see the source, drain and gate, this is mostly be there in this place of the channel and also the other portion. And why we need to go for the silicon on insulator the technology. So a MOSFET will be scaled down near to and also near to the submicron dimensions. As we go for the scaling of the MOS transistor, the small geometry is going to be alter the device performance. So the outcome of the MOSFET will have a some kind of the degradations due to because of the scaling. So there is some parasitic effects are there which will be pronounced here, and also it will be continuously miniaturize the device of the MOSFET, and also in the bulk technology point of view, these parasitic capacitances and resistance at the latch up will be always will be very high, and the compatibility of the fabrication point of view without any special equipment like without kind of the any special equipment, the existing will be help you to for the fabrication point of view, and also capability of the higher current densities, we can obtain the equivalent the bulk devices. So here you can see the parasitic capacitances in a transistor, as it is the NMOS transistor. We have a P type of the substrate. In general transistor I am talking about, and there is a scope in general transistors. There is a possibility of these kind of the parasitic capacitances across the source, across the gate to drain, drain to body, and gate to source, and source to body, and also the gate to body. So all these parasitic capacitances will be degrade the performance of the output of your the mass transistor when we go for the scaling further and further. So as the geometry will be scaled down and the device performance parameters will be degrade. So that's why we need to use the SOI to improve the output of the device performance. And also the conventional CMOS technology will have some sort of the limitations, or we can say some kind of the problems or the limitations. One is the short channel effect. Everybody knows that when the way you are reducing the channel length, you are going to have a more and more number of the short channel effects. Short channel effects are there are 4 to 5 short channel effects are there. All these are going to be effect on the length of the channel is reducing, and also narrow the channel effects are also will be having the another limitations in the MOSFET. And also latch up problems is the one of the very drawback in case of the CMOS, where we have a both NMOS and the CMOS. So in those cases where this SY technology will be always a better option for the researchers to do their work in case of the using the SOI based technology. So SOI based devices different from the conventional silicon built devices in that silicon junction is above an electrical insulator. So typically the silicon dioxide or the sulfur is used here, and here you can see that the base is the substrate where we have the very ultra thin buried oxide layer, and source and drain is the other side, and we have a gate. So based on this SOI, the technology, the SOI fabrication transistors are encapsulated with the SiO2 in all sides of the device. So conventional bulk substrate NMOS, and also we have a partially depleted silicon on insulator NMOS transistor, both the NMOS transistors, but here it is the SOI based technology is used. This here in this SOI technology, all sides are protected by this SOI insulator, and there is the channel is there, which is the floating body here. So that is one way there is a development in case of the transistor based on the SOI technology. And the choice for the insulators, because insulators are depending upon the intended applications, like you can take the sapphire, which is used for high performance radio frequency point of view, and also the radiation sensitive application. The radiation can be slightly improve in this particular case, and also silicon oxide is highly preferable because it is very much possible for the reducing the short channel effects in case of the silicon oxide. In most of the cases, silicon oxide is used for the microelectronic devices. So that's why you can see the comparison between the bulk device and a fully depleted SOI device, where we have these type of the advantages. And SOI MOSFET structure looks like similar to the MOSFET, other than this buried oxide. The buried oxide is the floating silicon film which is above this buried oxide, and the only thing is that the buried oxide layer where you will be placed, you are going to be placed, it is fully depleted or the partially depleted. Buried oxide film, I mean this buried oxide film, the thickness is going to be change the outcome of the device. And another thing is that the floating silicon film, where it is in the like a channel, which is leads to the floating body effects of the device. And based on that, when we have a bulk MOSFET and a silicon on insulator MOSFET, we can see the cross sectional view here, and also we can see the other the dimensions of the device. So here, which is mentioned in the left hand side, the bulk MOSFET, source, gate, drain, and also for the silicon on insulator MOSFET, it is almost all like as a similar terminals. But the thing is that the gate oxide layer is involved here, and buried oxide layer is also involved here in case of the both the SY MOSFET and bulk MOSFET. So we have a classification about this SY. SY is two types: fully depleted SY and partially depleted SY. So for an N-type partially depleted SY MOSFET, the sandwich of the material is the P-type film between the gate oxide and the buried oxide. So which is very large here. And the fully depleted SY is very thin and is fully depleted SY devices, so that the depletion regions will also be covered the whole film. So what will happen, the depletion region cannot cover the whole region in case of the partially depleted. So to some extent the partially depleted SOI behave like as a bulk MOSFET, but whereas in fully depleted SOI, the front gate, that is supports the less depletion charges than the bulk, so it can be increases the inversion charges which is occurring in the for the switching applications. And if you look into the one by one, the fully depleted SOI, it is a kind of the fully depleted SOI MOSFET, and in this it is a NMOS transistor where you are applying the positive voltage to the gate that depletes the body of the p-type charge carriers and induces the n-type of the inversion channels. And you see the depletion layer where we have this thin body avoids the floating voltage which we are giving. So the technology is designed to operate this way, which is a fully depleted SOI technology. And if the insulating layer of the silicon is made very thin, the depletion layer fills with the depletion layer fills with a full depth of the body, so that the silicon under gate is so thin that is fully depleted of the mobility of the charge carriers. There is no floating body effects will be occurred here. And the top silicon layer is between the 5 to 20 nanometer thickness is preferable, typically 1 by 4th of the gate length. And whereas coming to the partially depleted SOI MOSFET, here you can see the box, that is the depletion portion of the body, is not covered to anyone. It is the floating body is occurred here. The technology is here to operate this way. It is called the partially depleted, and here you can see if the insulating layer of the silicon is made thicker, the inversion region does not be extended to the full body, full depth of the body. So the silicon under the channel, here the silicon is under the channel, is partially depleted of the mobile charge carrier. So there is a avalanche ionization of the drain can be leads to the charge carrier accommodation in the quasi neutral region. Therefore this type of the partially depleted SOI, which is more close to the bulk MOSFET. And the differences between the partially depleted and fully depleted MOSFETs are: partially depleted SOI MOSFETs are insulating the box thickness will be vary from 100 to 200 nanometer, whereas fully depleted one, the thickness is 5 to 50 nanometer. The thickness of the box, that is the buried oxide layer, is very small in case of the fully depleted SOI. And the top silicon layer is 50 to 90 nanometer in case of the partially depleted, where in case of the fully depleted it is 5 to 20 nanometer. And the partially depleted SOI is more or less like a bulk the MOSFET. That's why it is used for analog circuits, whereas fully depleted SOI is used for low power applications and also some kind of the ultra low power applications. And fully depleted is having a impact on the leakage current and power consumption is very good improvement, whereas in case of the partially depleted it is easy to manufacture, but the leakage current and also power consumption is not appreciable. And the drawback in the partially depleted SOI is the packaging scalability is bit of difficulty, where the FDSOI is having a fabrication bit of complex process. So you can see the development of the SOI MOSFET, like fully depleted and partially depleted from the bulk transistor. So this is the bulk transistor where we usually we see normal case, and here we have the source terminal, we have the gate terminal, we have a drain, and there is the channel between the source and the drain in the form of the channel. And that is normally in the same kind of the material, that is the entire material is the silicon, or the silicon and other kind of the material. So, and here the channel forms in bulk silicon, whereas the partially depleted and fully depleted, you can see, observe that because of this buried oxide in both the cases, the body is partially depleted here. Therefore the floating point is independent of the bulk substrate, and the floating body boosts the performance, but induces the speculations like the kink effect, and also the history of the other specularities in this particular device. And whereas in case of the fully depleted, the buried oxide layer is fully depleted, therefore ultra thin body is completely depleted here. So the box can be optional to be ultra thin, and it is too small compared to the full partially depleted. And it can be addresses the scalability issues, and it can be addressed no kink effect here, and thickness of the silicon and thickness of the box is highly recommended into a very small scale. The advantages of SOI is another way is normally in a bulk CMOS transistors we will have the latch up problems will be occurs due to the glitches and all. But whereas in SOI CMOS this will be reduces the parasitic capacitances. Therefore SOI has no wells in the substrate, and therefore no latch up and no leakage paths will be occurred in the SOI CMOS technology. And also the better radiation tolerances will be happens due to the internal development of the charge carriers heat. So the soft errors in SOI and soft errors in the bulk SOI will be having the greater differences in case of the high resistivity in the substrate, and also due to the buried oxide layer. And also the another thing is the SOI CMOS will have its capacitances advantages, and because of that it will have a low drain and drain to source junction capacitances, and that will be comparatively small, where in case of the bulk transistors. And because of that the capacitance will be reduces greatly, which will be impact on the low power dissipation factor. So the wiring capacitances, gate capacitances, and also the other junction capacitances will be greatly reduces, which will be helped for the reducing the power dissipation. And also the better subthreshold swing in case of the SOI compared to the bulk, where because the single gate and the double gate will be always will be reduces the DIBL, and the subthreshold swing will be very steeper, and on current is bit of increases in case of the SOI MOSFET. So the limitations of SOI MOSFET, as I mentioned, it is the floating body effect, because silicon on insulator, it is a process of technology to be build the devices or nanoscale devices. The source body and the drain regions of the transistors always will be insulating from the substrate only. So the body of each transistor is typically left uncovered or unconnected. Therefore, that results in the floating body, and you can observe it from this particular the picture. The floating body can be get freely charged and discharged due to the transient, and these conditions will be effect on the threshold voltage, and also many of the other device characteristics like the drain current, and also electric field, and also energy levels of the devices. So so bulk potential decreases, but this case the floating body effect will be always a issue in case of the SOI. And the kink effect is also another issue, because the transistor which will be formed the capacitor against the insulating of the substrate, you can see the drain voltage versus the drain current, and here you can observe the charge which is accumulated on this capacitor, which may be cause the diverse effect. And here you see this is the region where the drain current will have the very slow development of the drain current, which will be for the produces for the leakage current point of view. So the current which is flowing through the devices is affected, which is based on the charge carriers accumulated on the floating body. So this itself will be called as the floating body effects or the kink effect, which is observed here in case of the SY MOSFET, and as a self-heating element, because internally the flow of electrons will be traveled from source to the drain. Therefore, SY transistor will have the surrounded on sides by oxide layer, which is created a self-container, and that will be enclosed, keeping the heat generating inside the box. So that is also another one of the limitations of this SOI MOSFET. So the fully SOI MOSFET using the TCAD, I am going to show you the code and also the outcome of the devices which we have run through the Silvaco. So this is the TCAD code for fully depleted SOI, and here we have a Go Atlas and mesh spacing dot multi is one we have taken into our consideration, and here it is showing the meshing statements where we have the X mesh and Y meshings to form your the workspace of your device, and later on we have defined the regions and defining the electrodes. We have here three electrodes: gate electrode, source, and a drain. And also we have the doping concentrations, the doping concentration of the source, drain, and the channels. And we have also given the contacts for that, and interfacing the quantization is considering as a charge density is 0 here. And we are defining the models and the methods, and here we have used the concentration mobility model, SRH model, Agur model, and BGN model, and FLD mobility model, and CVT model. So the method which we have used is the Newton-Raphson method, and the number of iterations we have considered is 10. And defining the output statements which is mentioned, the drain voltage is considered as 0.2 volts, biasing voltage, and the gate voltage which starts from 0 to 1.5. And by defining of all these given statements, one can able to see the Tony plot of the device, and this is the device which we have taken the dimensions of the x direction and y direction, and this is the fully depleted because here the SOI is on the substrate, and we have observed the drain current of this particular the device, and it is showing that the gate voltage which is starting from zero. As gate voltage is increases, the drain current is also slowly it is increases, but after the threshold voltage of the device the current is spontaneously increases and reaches to the saturation limit. And we also observed for the SOI MOSFET fully depleted point purpose the electric field of the device. We also mentioned the electron and hole concentrations of the device. We also seen the energy bands of the device and surface potentials of the device. And after that we also seen the for the same dimensions we have gone for the partially depleted SOI MOSFET by TCAD by using the silver code, and we have developed the code for these by mentioning the meshing statements and region statements, electrode statements, and doping concentration statements, and contact statements. Models and methods are incorporated here, and also the Newton-Raphson method has been considered here for the outcome basis of the device. This is the structure of the device which we have taken on the x direction and y direction by mentioning the source, drain, channel, and the gate and the required gate work functions. And we observed that the drain current here, electric field, electron and hole concentration, energy bands, and surface potential, and the comparison of these electrical parameters of the proposed device and the conventional device. So the parameters which we have compared between these two SY fully depleted and partially depleted, we also compared with the existing literature work, and we have observed there is some improvement in our proposed structure which we have considered as per our own structural orientation. So our architecture is a bit of change from the others existing literature. We obtained on current is 14.5 10 to the power of minus 4, where from the literature it is available 2.47 10 to the power of 4 and 1.5 10 to the power of minus 4, and off current we observed 4.36 10 to the power of minus 5, and where in case of this is 2.35 10 to the power of minus 5, and 8 into 10 to the power of minus 6, and on and off ratios also we have observed for both fully depleted and SY depleted. So based on the investigations on SY MOSFET, both on fully depleted and partially depleted, this research is contributes in the field of the MOSFET and the people who are working in these devices for the optimization purpose. We did some device parameters and the impact of the device performance provided for the enhancement in the semiconducting technology, and also we did as of now we did for the electrical parameters of the DC, and also we have done it for the RF and also analog devices. So we can we have used the Silverco Atlas, which has been given a good improvement in the device simulations for our device, and our device is having a great potential applications in kind of the VLSI integrated circuits. Thank you one and all, and this is the session which is on the SY MOSFET. SY MOSFET we have considered as fully depleted and partially depleted, and we have defined the structure. After the defining the structure, we have developed the code in Silverco, and we have run the code, and we have obtained the output performance parameters, and after that we have compared our device performance parameters with the existing literature survey. So with this, I hope this video will be useful to some of the researchers who are working in the field of the nanoscale transistors, or the sensor technology researchers, or the VLSI researchers who are working in the field of the devices. Thank you one and all.